explore the relationship between the angular distribution and the 3D reconstruction, and also the interplay between noise and angular distribution. So we start with an atomic model. So again, I'm using all the time this protein that is here. So it is the wild type penicillin binding protein 5 from Escherichia coli, and it is a small molecule, but it is 40 kilodaltons only. But still, as we said in our previous videos, it is not just the weight, it is the relationship, the signal to noise ratio. So as long as we have enough signal to noise ratio, we should be able to analyze it. So we start with this protein, and then we can see how the map looks like. So this is the normal appearance of a converted atomic model, where we see each one of the atoms. We can see the structure in 3D. So this is our structure in 3D, and so yeah, this is how it should look like. So now what we will do is to generate different galleries of projections. So one is uniformly distributed in the sphere. So if we look, for instance, at what is the angular distribution, we see that the angular distribution is pretty uniform, while these other three, they will be biased in some direction. So for instance, this one, most of the particles are coming from our top views, and then we have also all images except those in the top view. So the top view is less populated. You can see that it doesn't go to minus 25, and then we have also here only side views. So we have only side views, and yeah, if you look at the range, we have only side views. Okay, so with the perfectly uniform distribution, we should get a very good reconstruction, even if they are very few particles. So even if they are only 1600 particles, we see the structure pretty well. We don't see artifacts in any direction. So yeah, so this looks like the original one. And with the other two, so what happens if we only have side views? Only 300 side views, but still the reconstruction is pretty good, and we don't have any obvious artifact. We can see it in 3D again. If you think of this process in Fourier space, we have filled the full Fourier space, and we see the same as in the previous structure. So as the original PDB. So the same happens here when we have all kind of angles except the top 25 degrees. So again, the reconstruction, we don't see any artifact. And again, if you think of what we are doing with the central slice theorem in Fourier space, we are filling the full Fourier space, so we see the full structure. What happens here? If we only have top views, we have the top views from 0 to 25 degrees. Now we look at the structure. From the top view, we start to see some kind of artifact around. Can you see? Here we have a kind of halo around, and some of the slices are very good. The central slices are very good because we have a lot of top views. But when you look from the side, you start to see problems. So missing information, because we are filling only a part of the Fourier space. So missing information results in this elongation. So this is because of the missing information. Okay, so that's good. We understand that now. And now what happens when we add noise? So, or when we put both together. So let's say that we put both together. So we have a uniform distribution and views, more views from the top. And this is 1 in 4 if you want. So 20% of the particles have a uniform distribution, the other 80% are coming mostly from the top. So should we expect any deformation? Because this one is creating an elongation. In principle we shouldn't, because we are filling the full space. So let's see if that is true. So if we now reconstruct with the full data set, we see the original PDB. So no artifact, no elongation. We can check in 3D, but there is no elongation because we are fully covering the 3D space, and then the reconstruction algorithm will give more or less weight to each one of the samples depending on how many samples are coming from that direction. So there is no obvious elongation here. There shouldn't be. And now let's add noise to the particles, because here we are using perfect angles. Let's add noise, but very little noise. So these images are not perfectly clean, so there are fluctuations in the background. You see the numbers here, down here. So you see that they are not perfectly clean, but they are pretty clean. So the signal to noise ratio is huge. So we estimate the angles. So now the angles have to be estimated from the data, and we reconstruct the resolution. The claimed resolution is pretty high, and when we look at the structure, again we don't see any deformation. So, and we can check in 3D. So having an overloaded direction in principle shouldn't create any problem if we have enough signal to noise ratio. So here we see that the structure is correct, and we can check how many for how many images we have made a mistake. So you see that our uncertainty is in the order of 2 degrees, and in shift it is less than a pixel. So we can check, for instance, in the angles, and the angles here, for most of them we did a very good job with a very low angular error, and then for a few of them, for a fraction of them, that is about 10%, 15%, we have made much bigger mistakes. And despite the fact that these images are very clean, really clean. Okay, so now let's put it in a more realistic setup. So now we will have a low signal to noise ratio, we have overloaded directions, and then the problem is if we use perfect angles. If we use perfect angles, the fact that we have noise and overloaded direction, let's see if it causes problems. We don't see, well, there is a lot of noise, but this we already know. But if we filter, for instance, let's filter at 4.5 angstroms, we see the structure pretty well, and it doesn't seem to be particularly elongated. We can check that in 3 dimensions. Yeah, we have a lower quality structure, but that is expected because we have more noise, much more noise than in the other case with a very high signal to noise ratio. So we cannot recover the high frequency component so well, but otherwise there is not any particular elongation. The problem comes when you have overloaded directions, you have low signal to noise ratio, and you have to estimate your angles. Still we can check for how many angles we did it right. We'll see the result of the map now. So for how many angles we did it more or less right, it seems that we did it more or less right for many of them, and the error is not that high. It is 7-8 angstroms, which is enough to blur it quite a lot. But what we will see is that this blurring is not uniform. So the blurring occurs mostly at the top views. So when we look at the structure, the claimed resolution is 6.5, but when we look at the structure, okay, so in principle it seems to be correct, but when we make slices in the other direction, we see something strange here. It seems that in this direction, that is the direction of the top views, we don't have enough resolution. So now if we look at it in 3D, what we have is that this is our structure. So you see we have this elongation problem again. So the elongation problem is actually an interplay between estimating angles and having low signal to noise ratio and having overloaded directions. So these overloaded directions will tend to attract particles around, so more particles than actually coming from the top view are estimated to be there. So we can see that in the angular distribution. So in the angular distribution, we see this is not so easily seen because of the scale, but let's see if we can have a different representation of that. Yeah, this one here. So we have many more than we should, and there are some mistakes, especially here in the central area. And also, yeah, let's look at it. I think no, I want it in this way. So this is this view, this 3D view, where we have top views that are much more frequent than the rest. Okay, so this is a problem of signal to noise ratio, overloaded directions, and having to estimate the angles. So by itself, having an overloaded direction shouldn't cause any problem, and reconstruction algorithms can handle the different densities of points. But when you have to estimate the angles and you have low signal to noise ratio, you are more prone to make mistakes along the overloaded direction, because it is gaining signal to noise ratio and then it is attracting more particles around. Okay, so with this we finish this video, and I hope that we now understand better what is the interplay between angular distribution and overloaded directions.